So for those of you who have taken any portion of calculus in the past, derivative is a really big topic, and you probably remember that word at least quite well. And we're going to encounter this today in section 2.1. This is the derivative and the tangent line problem. However, it's not until 2.2 that it's the part that you remember most likely or most well. So let's take a look, and this is a little bit at the beginning, what we've actually talked about before, that is the secant and tangent line problem. So on the first day of class, I drew you some pictures of secant lines and tangent lines, and we're going to draw those again right here. So if you'll remember, a secant line, so we're going to draw our curve something like this, and we're going to take our C value, we'll put it right here. And over here on the y-axis is f of c. So there's our function value, f of c. It's maybe a little bit high, but it's not too bad, and c. And what a secant line is a secant line is taking some other point. So, whoops, we'll go right here. And this point right here, it's another point. I mean, I could use another letter, but I'm going to say it's at distance h. So this point is c plus h away. Right? It's c where I was before plus the h. And it's got a corresponding y value somewhere around up here, f of c plus h. And what we're doing is we're creating a line between these 2 points. Bear with me, I'll move my line. Here we go. That's a secant line. You have 2 points on your curve, you connect them with a line, and you can create a secant line. The slope through the points c, f of c, and c plus h, f of c plus h is given by this equation at the bottom. Right, so we change in y values. Well, I've got f of c plus h minus f of c on top. The change in the x values, which is c plus h, and c on bottom, which is h. And it simplifies into f of c plus h minus f of c over h. Okay, change in y over change in x. It's just slope. So when we're working at a tangent line, what we're wanting to do is we're wanting those 2 points that are right now a little bit far away, they're h away from each other, to approach and become closer together. That's what a tangent line does, is it's finding that line as those points become infinitely close together. So visually, I've still got this screen I'll draw it on, and then we'll go to the next screen to do our definition. We have the same curve we did before, roughly speaking. I have my same point C here. And here was my point originally. So I realize my graphs are not perfectly the same. Okay, but that's fairly close to what I had before. We're going to go with it anyway. And what I want is I want these points to be closer. So I'm simply going to shift that point that was h away to being a little bit closer. And if I do that, then my line becomes that one, right? The line is different. And if the point gets a little bit closer, say like right here, then my line becomes, I can't draw today very well, this one. And if my point gets a little bit closer here, then my line will shift and it will become this one. So the line keeps changing as the points getting closer and closer together, but eventually it stops changing very much because the points do get closer and closer together. So if I went and did one more, I'll draw it in a different color because this is going to overlay it right here, and I were to redraw the line again. Can you see that red dot at all? I want to make it really big and fat. It almost looks like it's on the last purple line I drew, right? Eventually the points become really, really close together, and it doesn't really change a lot in what that line that I'm drawing is. So what happens is f is defined on an open interval containing c. That should sound like something we've seen before. It was just on your test. then what we're taking is we're taking that f of c plus h minus f of c over h. This is the same thing we just had on the previous slide as the slope of the secant line. The part that's new is the limit part at the beginning. The part that says that this distance between those points is becoming close to 0. In other words, the points are getting infinitely close together. Then this slope will exist. Then the line passing, if this slope exists, then the line passing through CF of C with slope M is the tangent line to the graph of F at the point CF of C. So previously we called it a secant line. Now as we let these points get infinitely close together, it creates the tangent line. And the point CF of C is also called the slope of the graph. So if you hear slope of the tangent line or you hear slope of the graph, those words mean the same thing. So slope of the tangent line and slope of the graph. The reality is there's some other words that mean the same thing as those as well, and we will add those sort of to our list of equal statements as we work our way along. Right now we're finding slopes of tangent lines, slopes of graphs. Okay, so there are notes posted online. If you're having difficulty, I would strongly encourage you to print those off because we can't have time to write them all down, so they're posted. We're going to find some slopes of tangent lines. So we have a function. It's a parabola, right? You basically know what this looks like. It's parabola opening downward because it's negative x squared. It's got a y-intercept of 6. Definitely is not linear. If I find 2 points on it and I connect them with a line, it's not going to be the graph itself, right? It's going to be not this graph, but it's going to look something like this where I've got a curve. So how do I find the slope value? Oh, there's one more thing I think that I didn't define. Let me put it over here, actually. This slope also can have a new name. It looks like f prime of C. I'm going to use that notation here. So this notation, or so this slope that I'm finding is g prime of C, and my C value is 1, so g prime of 1. So this is the slope of the graph, or slope of the tangent line. And the directions said over here that I'm going to start out with a limit. And you guys just discovered again that notation is necessary all the way until the very end when you plug the value of 0 in. So there's going to be a limit as x approaches 0 all the way along. And you're going to have your equation G evaluated the C value that you have of 1, right? It's the x value of this ordered pair 1 plus h minus G of 1 over h. And I'm simply getting that from this definition right here. C's are 1s, so I'm just rewriting this notation. My function's name is G, so I wrote G instead of F, and my C value is 1, so I wrote 1 instead of C. So all I've done is rewritten that same definition with the 1 in there and a G of x instead of an H of x, or instead of an F of x. All right, so this is the point where you have to remember a bit of the algebra skills that you worked with probably at least a year ago in terms of this notation. G of 1, I think you're probably okay with. Can you tell me what G of 1 is looking at this equation? It's 5. Hayden, how did you decide that it was 5? There's a couple of different x
squared, so 1 squared is 1, 6 minus 1 is 5.
Okay, so you plugged the number 1 in, right? Absolutely. And we can definitely do that on that one. There's actually a really nice fact right here is they told us it was 5 here too. So sometimes your problems will give you the ordered pair and it gives you the y coordinate, and sometimes they don't. Okay, so this one gives you the y coordinate. If it didn't, you can do exactly what Hayden did. Super easy, plug in the number 1 into x, evaluate it, you get 5. So taking a look at what we have over here, that shouldn't say x, I'm so sorry. Those need to say h. Please fix them if you were copying what I had. h approaches 0. Okay, so I have g of 1 plus h. Actually, I'm going to leave that blank. I'm just going to write down that this is 5 at the end. So minus 5 over the h. Okay, that's the easy part. The ending part's the easy part. The part at the beginning, g of 1 plus h. All right, so when I found g of 1, actually when Hayden found g of 1, what he described is taking where the x was in the equation and replacing it with 1, correct? The same thing happens with 1 plus h. I find where the x is in the equation, and I replace it with 1 plus h. Well, my equation says 6 minus, and then it has an x that I'm going to replace with 1 plus h, and that x is squared. So this component is coming from taking this equation and replacing the x with 1 plus h. Is everybody okay with that step? Okay. After that, we're simplifying with some algebra. Now, there were several places that were very concerning about some algebra things happening on your test. This is one of those places where there are sometimes concerning things that happen. 1 plus h squared is not 1 squared plus h squared. Okay? You have to multiply it out by itself. So, I have 6 minus 1 plus h times 1 plus h minus my 5 over h. And I actually have to multiply out 1 plus h times 1 plus h. So what is 1 plus h times 1 plus h? What's 1 times 1? 1. What are my inner and outer terms if I do those? Yep, 2h. Yep, and then my last term would be h squared. You'll notice I kept mine in parentheses just because I didn't want to accidentally forget to multiply it through by that negative. If you can do that at the same time, that's totally fine. You notice then that some things start to collapse, right? They combine. So I have 6 minus 1 minus 2h minus h squared minus 5, and all my constants combine to become what? 0. And that will always happen. If you end up with a constant still in the numerator, you've got an error somewhere in previous work. Okay? So all of those pieces that are currently highlighted in red add to 0. And what you'll notice is that everything that remains has a factor of h in it, right? Again, that will always happen. Let's see if I had another slide. I don't. So, we end up with the limit as h approaches 0. I can factor an h out of the numerator. So my numerator is now factoring out an h, negative 2 minus the h, divided by the h, and I'm able then to cancel my h's. We're super close to done at this point because the h in the denominator was exactly the problem. It is what I did was not allowed, it was what was not allowing me to plug in 0, right? The h in the denominator was the problem. And now I only have a negative 2 minus h, and can I plug 0 into that? Absolutely. What will I get if I try? Yeah, negative 2. So my slope is actually equal to negative 2. Grab your calculator out. I want to show you a cool calculator trick. Are you ready? This is cool stuff. Now, it doesn't replace all the work you just did. You got to show me the work. But I'm going to show you how you can verify that you got the right answer. You all know that you like to do that. Don't look at me like she's just crazy. You know. All right. I'd like for you to enter your equation into y1. Okay? Enter equation into y1. So what was it? 6 minus x squared. And then go back to the regular screen where you can, add, subtract, and square root and all that good stuff. Regular screen. Okay, so inside your regular screen, I want you to hit the button that says Math. It's on the far left side of your calculator. It says Math. And when you do, you see a list of options like frac, decimal. There looks like a cube and a cube root and an x root, a whole bunch of stuff. Do you guys see that? Okay, go down to option number 8. And what does option number 8 say on your screen? Inderiv. Okay, now I mentioned earlier on that these are called slopes of tangent lines and slopes of curves. They're also called derivatives. That's what we're finding. We're finding a derivative. So if you select option number 8, your screen will look one of two ways. Your screen will either say, let me show you what my screen says. Your screen will either say inderiv in a parenthesis. This is the older operating system that I have. Or what does somebody who doesn't have that say? Who has a newer operating system? It's not showing up there when you hit enter. Yours read? Okay. So let me show you because I can never remember what it actually looks like. Or it looks like this. And it's got this little box here that's sort of like dotted. And then it has a filled in box and another dotted box. Okay? So it looks one of those two ways. Does everybody's screen look like one of those two options right now? Cool. Okay, so let's do the one that's on mine first. So here's the notation that you're going to want to use. I'll show you where everything comes from, but jot this down in your notes if this applies to you. You're going to tell it y1, comma x, comma, and then it's going to be whatever your value is that you're plugging in. We plugged in the number 1. Okay, those of you who have the other one, like Reed showed me, yours actually says you're going to plug in an x here. You're going to do your y1 here. You're going to do your x here, and you do your 1 here. So you're using all the same things that both versions are using the same notations in a different way. So I think you probably know where to get the 1. Calculator, you see where the 1 is. You know how to get your x's, right? Because you've plugged things in graphs. The thing that you may not know how to get is the value y1. So where do you get the value y1? Well, you get it underneath the vars key. So vars, and then you click on yvars, and then you click on function, and then you click on y1. And all of this is under Math 8. So if you click on Math 8, and you use either of these versions, and you tell it that you're using the equation y1, that your variable is x, that's why those x's are showing up there, and that you're evaluating it at the value of 1, and you press enter, your calculator should tell you that the slope is -2. Did anybody's not work? It gave you an error, or it gave you some other value. So everybody has a -2 who has the calculator to try it with today. Awesome. So this means you can verify that your answer that you got is right. But of course, you're still going to show me all the work along the way, or at least a good portion of it. You may be able to simplify some of the algebra as you go, but it's a good portion of it. Any questions on this? Okay, so this is all well and good if you're only interested in finding the slope at the one specific value of 1. But what if you were asked to find the slope at x = 1, and x = 5, and x = 17? Well, if you do it this way, you're going to have to do it 3 times, right? Like you have to redo the whole process with the new value. You have to put the new values in a different place. Everything has to sort of be redone a second time. Well, it would be really nice if we could do it in general and just evaluate it at the point I care about at the very end. And in fact, we can. So this is the definition of the derivative of a function in general, not just at the point value c. You'll notice much of it looks the same, right? I've got that same notation that I talked about before. It's got that prime. I still see that limit as h approaches 0. I still have f of, in this case now instead of c plus h, it's x plus h, minus f of x instead of f of c, and it's still over h. And it tells you at the end that this works for all x for which the limit exists. Now we know that the limit doesn't exist on every function everywhere, so that's saying, like if there's an asymptote, this isn't going to work. If there's a jump in the graph, this isn't going to work. But at all the other points, right, everywhere else it's going to work just fine. As long as there's a limit, this is going to work. And that f prime is a function of x itself. So we should take a look at one of these, right? And see how it differs from what we just did. Because it should be mostly the same. And in fact, to be honest, I think it's even easier than the one we did before. I think that plugging in that number of c equal 1 at the beginning actually makes it look messier than the other one. But that's my take on it. So we're going to give it a try, you can see. All right, so notationally, just like before, we're going to write down f prime of x equals the limit as h approaches 0. My function this time is actually called f, so it's f of x plus h minus f of x over h. So the problem always starts out this way. I don't put in a 1 for x like I did a 1 for c, okay? It's just in there generally. Okay, they're pretty good so far. Now, you already know what f of x is. It's the equation you were given to begin with. So just like with the other method, the second piece is the easier of the two to replace. It's 1 over x squared. So all of that you can get for free. The earlier part, right, the f of x plus h part, is again telling you, take your equation, and everywhere it has an x, replace it with x plus h. Well, in this equation, there's only one x. It's right here in the denominator. So I have the numerator's a 1. The denominator was previously x, and now it's x plus h, and it's squared. Okay. The thing about this problem that makes it messy is because now I have fractions inside of fractions. Y'all see that, right? We call them complex fractions. Like officially it's called that, not just because it's complicated. It's really called that. And yeah, it actually is really ugly. And the problem is actually that h on the bottom, right? That's what's causing all of the problem here, is that I can't do anything until I somehow get that h that's in the denominator to cancel with something. I mean, that's my real goal. Got to get that h to go away. So we need to not have the complex fractions. I'm teaching a college algebra class right now. It's the same thing I tell them. I don't want fractions inside of fractions. I need to manipulate and simplify so that I end up with simply one numerator and one denominator, right? So we're going to do that. We're going to get one numerator and one denominator. Now, in particular, one way of doing that is to clean up the numerator first, because it's got the two pieces, the two fractional pieces. It's not the only way of doing it, but I think it's a pretty good one. So we will start with the numerator fractions. And as you know, in order to get the numerator to have the same denominators, right, the fractions to have the same denominators, because these denominators don't match, we'll have to multiply them by one another. So it looks something like that. So the first piece will have x squared. Then I have this subtraction sign right here in the middle. And the second piece will have x plus h squared. It'll all be over x squared and x plus h squared, which happens to all be over h. Okay, here's the deal. Let's pretend that I was dividing by the number 7. Dividing by 7 is the same as multiplying by what? 1/7, right? Multiplication and division are reciprocal properties, right? So dividing by 7 is the same as multiplying by 1/7. So while, yes, dividing by h here is correct, it would actually be a lot easier if instead I multiplied by 1 over h. And it's the same thing, right? dividing by h is the same as multiplying by 1 over h. But multiplying fractions is actually quite friendly, because when I multiply fractions, I just multiply the components, right? So the denominators just all get multiplied together. Now, we need to clean up the numerator still. So let's take a step to do that. But my denominator, okay, I'm still messing up my x's. These are supposed to be h's. I just did one of them. H goes to 0. Okay, but my denominator will simply be x squared, x plus h squared, and h. That's what happens when I multiply them all together, and I don't want to multiply them out. We talked about that before when we did limits. It's typically not helpful, especially if my goal is to make the h cancel with something. I don't want to distribute the h through. That will be much more difficult to see the cancellation. So I'm going to leave it in factored form. The numerator I will need to distribute out. So I've got x squared, and then I need to do x plus h quantity squared. And again, that's not x squared plus h squared, right? I have to multiply it by itself. So what do I get when I multiply x plus h times x plus h? X squared. Fabulous. And all of that is negative because of the negative before that quantity, right? So each of those pieces are going to be negative. Now, the beautiful thing is that, do you notice what happens to my x squared? Yep, it's going to cancel out. So I have x squared minus 2xh minus h squared. And maybe you could combine that with the previous step. If so, that's fabulous. But these two add to 0. And then everything that's left in the numerator, just like the problem before, has a what in it? An h. And if we did it right, that always happens. Always. It has to. Otherwise, I don't stand any chance of canceling the h in the denominator out, which is the whole point. So continuing with this one, I will have an h that I can factor out. I have negative 2x minus h still in the numerator. I have x squared, x plus h squared, and h in the denominator. And my h cancels out. I'm going to rewrite what I have just because it's awfully tiny and I didn't mean for it to be that way. I'm so sorry. But what I really have left here now is negative 2x minus h over x squared x plus h squared. Those are the pieces I have left after my cancellation. I don't know about you, but I don't really want to multiply anything out. I really just want to plug 0 in. Yeah? And wouldn't that be easier? 0 is great. 0 makes things disappear. So if I can plug 0 in, I'm definitely going to do that before I do any more simplifying. So sure enough, if I plug 0 in, I've got negative 2x minus 0. And I've got x squared and x plus 0 squared. So my numerator ends up being negative 2x. What's my denominator? X to the 4th. Do you see anything that simplifies? Yeah, one of the x's cancel out with the numerator, right? And so this piece right here ends up giving me negative 2 over x cubed. And that is the derivative or the slope of the tangent line for any point. So if this were the problem before and we wanted to know what happens at x equal 1, I can now plug number 1 in. And I can plug 5 in and I can plug 17 in as well, or however many different slopes I'm trying to find at any general x value now. Now, the caveat to that is that you can't check the equation with your calculator. It doesn't do that. Now, there's some other things that we'll do. I'll show you calculator tricks as we go along the way, like I just did that earlier one, but it involves you actually plugging in a value for it. And I don't have a value to plug in on this one. I'm only doing it in general. All right. We're going to try another one. So the first one we did, this one over here, was a polynomial, right? A quadratic, specifically, parabola. This one was a reciprocal. It was a rational function in particular. And this one's a radical function. So I wanted to give you a variety of problems so you could see how they work in a variety of ways. Now the directions have changed a little bit, but we still have to do the things we've been doing already. We just have to do a little bit more at the end. This one wants us to find an equation of a tangent line to the graph of f at the given point. So think about what you know about lines. Can somebody give me a general form of a line that you remember? Y equals what? Mx plus b. Okay, so in order to use this equation, I need to know the slope, right? And I need to know either the y-intercept or some other point on my graph. And I actually have the point on the graph, 1, 1. So the only thing I don't have is the slope, and we're in luck because that's what derivatives are. They're slopes. Slopes of tangent lines, and we're trying to find a tangent line. So as I go through and I find this derivative, this slope of the tangent line, that's exactly what I need in order to finish the equation that I'm supposed to be trying to find, y equal mx plus b. So if you kind of think about it in this way, the first thing I need is I need a slope, and I'm going to get that by finding f prime of x, or g prime of x, or whatever. This one is f. I need a point, but I am actually given the point 1, 1 on this problem. And then I'll be able to find y equal mx plus b with those two pieces of information. So I need to find the slope. So we're going to find our slope, our f prime of x, and we're going to do that with this limit definition. So the limit, as h approaches 0, of f of x plus h minus f of x over h. But my function's a radical function. All right, so every step I will write down limit as h approaches 0 until I actually plug in 0. Again, the second piece is the easy one. It's the piece I'm given. It's minus square root of x. What will the first piece be? What is f of x plus h going to be? Yeah, square root of x plus h. I replace x with x plus h. And now I hope that you see maybe part of why we worked so much on radicals in chapter 1 and how to simplify things. Because you already know how to do this. What do you do to get rid of the radicals that are going on the numerator? Conjugate, right? I multiply by the conjugate. So the conjugate, of course, is the same thing I have with the opposite sign in between. And if I do it on top, I have to do it on bottom as well. Okay, so the whole point in multiplying by the conjugate is that I actually do get to multiply just the first terms together. That gives me x plus h, and the last two terms together, which will give me a negative x. Yeah? Negative because one's positive, one's negative. X because I've got the square root of x squared. And again, like we talked about before too, I don't want to simplify, or not simplify, but I don't want to distribute or clean out or whatever the denominator. I want to leave it factored. What beautiful things do you see happening in that numerator? Goes that to 0, right? And I have a h left in my numerator. So I can factor this h out. It cancels or reduces, right? So what am I left with in my numerator? 1. 1 is great. And in the denominator, I have the square root of x plus h plus the square root of x. And I know it sort of feels like, okay, but I still got radicals just there in the denominator now. But the reality is that it's better because I can evaluate, which was the real goal. I want to be able to plug 0 in for h, and I can now. I simply replace the h with 0. So what I have is 1 over, and there's 2 square root x's. And I actually don't care about the function. I'm looking for a slope, right? Specifically a slope at x equal 1. So I did all that work so that at the end I could evaluate it at x equal to 1. So now I have 1 over 2 square root of 1. And what is 1 over 2 square root of 1? One over 2, right? Square root of 1's nice. It's 1/2. This is my slope. So I have a slope of 1/2. I have a x value of 1. I have a y value of 1. I should be able to find b. Agree? 1 is equal to 1/2 plus b. What's b? Somebody's, it's 1/2. B is 1/2. So my equation of my tangent line is y equals the m, the slope was 1/2, x plus the b value I just found, right, was also 1/2. So my equation of my tangent line, the actual answer to my question, is y equals 1/2 x plus 1/2. Okay, grab your calculator, because I want you to at least visually check that that seems reasonable. So in your calculator, you're going to put the equation that you were originally given, which was the square root of x. And in y2, you're going to put the tangent line that you just created, 1/2, or you can use 0.5x plus either 1/2 or 0.5. So you're putting this into y2, and you're putting this one into y1. Okay? You can use your standard window if you would like. It's fine, but you really don't need any of the negative values. So if you would prefer, you can make your x minimum 0 and your y minimum 0, and then your x max and y max being 10 will be okay. And what you're going to see, I wish I could display, but I can't get this Elmo to work very frequently, so I'm not going to try. What you're going to see, I do have some space over here, is a graph that looks something like this, right? That's the square root of x graph. And you're going to see a tangent line that looks something like this. So that doesn't sort of like concretely verify that you absolutely got it right, but at least if it looked really wrong, you'd know there's something really wrong. Yours probably looks a little bit flatter than my graph right here. But did it look like that on your graph, roughly speaking? So it's at least plausible that it seems reasonable, right? I'm not sort of red flagged that there's something weird and wrong going on from the picture that I get. All right, any questions on that one? Let's talk a little bit about when slopes, specifically derivatives, don't exist or tangent lines don't exist. There are 3 places where derivatives do not exist. One is at discontinuities, and there are 2 types of discontinuities this is referencing. Holes, well, we can talk about 3. Holes, jumps, and asymptotes. So obviously, if you have a hole in the graph, notice back at the original definition when we talked about it, I said, doesn't this look familiar, except it doesn't say, except possibly at C itself? It has to actually exist there. If the function doesn't exist, if it's discontinuous, there's no derivative. Clearly, if there's a jump in the graph, and if there's an asymptote. So any of those problem spots, discontinuities, are going to create places where derivatives don't exist. And that was sort of enough to check, right? For the intermediate value theorem, or for other pieces, we were looking for continuity, and it was enough for us to know, is it continuous? And as long as it was continuous, we were good to go. Problem is that there are some continuous functions that also have derivatives that don't exist. So one of them is sharp turn. So if you had a graph that looked like this, and it has this sort of cusp or a sharp turn on it, there's no tangent line there. And I'm just going to argue sort of visually why that would be reasonable that there wouldn't be. If I were drawing tangent lines over here, tangent lines would look something like this, right? My purple line. But if I were drawing tangent lines on the other piece, they would look something like this. And eventually, as those points get closer and closer, those tangent lines get closer and closer, and it starts to look like all of a sudden now maybe I've got something vertical going on. Maybe. Or maybe not. It just there's a problem with the fact that those tangent lines don't approach the same slope. One tangent line becomes very, very positive. The other tangent line slope becomes very, very negative. And then the last one is a vertical tangent line. Again, we don't see it happen very often. There is an example at some point this semester. But if you had a graph where we have a vertical line that's a tangent line, the tangent line exists, but if you'll remember, the slope of a vertical line is undefined, right? So the slope doesn't exist. The tangent line exists, but the slope doesn't. It has the equation like x equals 4. It's a line. It just doesn't have a slope. All right, I have one example of how cusps show up. That's the second one, those sharp turns. And it actually occurs on problem number 4. One theorem before we get there is about differentiability. Differentiability applies continuity. What it says is if your function's differentiable, then you know it's continuous. Unfortunately, it doesn't work the other direction. Just because it's continuous does not always mean it's differentiable. And the number 2 sharp turns and the number 3 vertical jumps above prove that. I can be continuous and have a sharp turn. I can be continuous and have a vertical tangent line, but that doesn't mean that I have derivatives everywhere. But if I do have derivatives, I do know that my graph is going to be continuous. So let's take a look at this last example in section 1. It says, describe the x values for which f is differentiable. I don't know if you guys know how to graph this or not. Do you know how to graph an absolute value? Have you seen that before? Let's check that real quick just in case you haven't seen that, because I think that's probably the best way of thinking about this graph. So inside of y equals, clear out what we had from before. If you hit that same math button that we did earlier, and you just arrow over. So along the top it says math, num, cpx, prb. Do you guys see those prompts along the top of your screen? One of the prompts says num, num, and it says abs, or it may actually have absolute value symbols in the newer operating system. So if I click on that, and then I can put in x squared minus 9, and just the standard Zoom 6 window should work just fine. And what you'll see, and I'll describe why you see this too, is a graph that looks something like a W. Okay, so your graph looks something like that? Yeah? Okay. Imagine, if you will, if you took this piece and you flipped it down below. What would the graph look like? A parabola, right? If you didn't have the absolute values on this, x squared minus 9, it'd be a parabola, agreed? Opening upward, and hitting the y-axis at 9, negative 9, right? I mean, that's what it would be. So what happens when we take absolute values is that everything that's beneath the x-axis flips up. So that's why we end up with this sort of, hump in the middle here, is because it's everything that was below the x-axis flipping back up atop the x-axis. The reality is that there are two locations here now where I have sharp turns, agreed? They're right here. Those two places have sharp turns, and so I won't have derivatives there. Everything else is good to go. Everything else is nice and smooth and all good, but those two places are not. So I need to figure out where those places are. Any ideas by looking at the equation? Somebody said it. Was that you, Hayden? Oh, Tanner. Yep, you're right. How come? So in particular, the 3 and negative 3 would give me an absolute value of 0, right? Hence, I would hit the x-axis. That's where my y values are 0. So yeah, these are my two x values for which I don't have a derivative. Everywhere else I'm good to go, but not those two. Any questions on that? Okay.